All right, so we are looking at this process of optimizing exchange, and as I said, we really need a difference in the amounts of oxygen and carbon dioxide here. So the surface area is pretty high because you have all these extremely folded, like I said, there's about 70 square meters of tissue that make up your lungs. So you got that one covered, but of course, if you have a disease that you lose alveoli, or they collapse or they expand, like an emphysema, this decreases your exchange. All right? And then the distance or thickness of the membrane, as I mentioned already, the further you have to travel as oxygen and carbon dioxide, the less likely that you're going to get good exchange. Because remember, the blood isn't stopping here, it just keeps on being pushed and moved. All right? So, again, external respiration, oxygen in, right, and carbon dioxide out. As this deoxygenated blood from the right side of the heart reaches the alveoli, there is low partial pressure of oxygen because it's been out in the body, right, and the cells have been using it. So low concentration of oxygen in the capillary, high in the alveoli because you just inhaled, right, and you've enriched it. So about 104 is your partial pressure here. It's probably around 40 or less here. So oxygen will come in from 104 to 40, and it'll move on in to the blood cells, many of it, which will bind to the hemoglobin. And I said a little bit of it dissolves, as they show you here and here. The blood is high in carbon dioxide because, again, it's been out in the body, and it's now been, the cells have been dumping carbon dioxide in here. So high in the blood and low in the alveoli because it was low in the atmosphere. And so here we see the carbon dioxide is moving out. So some of it had bound to hemoglobin, some of it had dissolved in the plasma, and quite a bit of it, and that's why you see these three arrows, quite a bit of it had actually been converted to, again, these acids, carbonic acid, and then bicarbonate and hydrogen. All right? So internal respiration, so here's the cells of your body, right? So out that blood, now enriched in oxygen in the lungs and decreased in carbon dioxide because of external respiration, returns to the left side of the heart, and the left side of the heart just pushes it throughout the body, right? Systemic. So now these blood cells and plasma are carrying these gases and different amounts of these gases, and we're coming to these cells, and cells who have been doing cellular respiration, so have been using their oxygen and been building up carbon dioxide. So we say internal respiration between the blood or systemic capillaries and the tissues or cells of the body. And we want to move oxygen into the cells and carbon dioxide out. It's still about all those, it's still diffusion, so it's still all the things that govern diffusion, partial pressure differences, distance, right? And it says, again, this partial pressure difference is maintained because the cells of the body will constantly use oxygen, so they will always be low. Oxygen will always be low in the cells compared to the blood. And the systemic capillaries then deliver this oxygenated blood, which has high concentrations. Carbon dioxide is the byproduct of metabolism or cell respiration. So the cells in the body are always high in carbon dioxide, while the blood, which is not doing metabolism, it's low. All right? So that's your external-internal exchange. How did we move these gases? So we talked a little bit about solubility, but and partial pressures, but let's look specifically at the mechanisms I mentioned previously, about hemoglobin and so forth. So blood transports oxygen and carbon dioxide between the lungs and the cells of the body. So as they enter the blood, they dissolve in the plasma, and we saw that on the cartoon, or they combine with other atoms or molecules. And here we're really talking about either hemoglobin or carbon dioxide combining with water to make carbonic acid. All right, so oxygen transport is really, about 98% of this is going to be through hemoglobin. And that's because oxygen is not highly soluble, right? It's low solubility. It doesn't like to be in liquid form. It likes its gaseous form. So you have to attach it to this. And of course, you attach it to these iron atoms on this molecule, heme. And when it's attached, it's fully attached, there's 4 places per hemoglobin. We say it is saturated And so when all four have attached, it's saturated, or we say 100%. All right, so, and again, here's an important fact. The amount of oxygen determines how much loads. Okay, so here in a situation where you are in a highly enriched environment of oxygen, which is just normal atmospheric, nothing has changed for your atmosphere, healthy atmosphere, right? Then there's a nice amount, a very high amount of oxygen in the environment, and this is a difference between the body, and so this pushes the oxygen in. If you go to an area that's depleted in oxygen, right, or a higher altitude where the pressure is less, it's going to be harder to load, right? In other words, it's harder to move the oxygen in because partial pressure or amount of oxygen between these compartments is important. The chemical bonds between oxygen and hemoglobin are temporary. This is an extremely important point that often gets missed in the sense by, it's obvious though when you just reflect on it. Hemoglobin's not using the oxygen, it's carrying the oxygen. So at some point it has to pick it up and it has to let it go. And we have to figure out how it's going to do that. And we want it to really meet our needs, really, if we want to be honest about it. And luckily this is a brilliant protein and it does. But understand, again, can't hold on to it. So this is please consider this in a molecule like carbon monoxide. This is why it's a huge problem to your existence and continued existence, because carbon monoxide binds to hemoglobin as well, but hemoglobin doesn't let it go. In fact, it binds about 200 times more effectively, or we say with more affinity, than oxygen does. So, and it competes with oxygen. So pretty soon you have this molecule that you can't use in your body, but it's taking up all the places on this wonderful molecule, hemoglobin, and it's not coming off. And you die. So that can't happen with oxygen. We have to pick it up in a place and we have to let it go someplace else. All right, so here's what this looks like. Oxygen dissociation or unloading. All right, and again, you're not going to repeat this graph to me, but this is looking at the amounts, because we said that's a really important thing here, is how much oxygen is there in the tissue. All right, and this of course is how much oxygen is still bound to the hemoglobin. So if it's 100%, then we say all four binding sites are taken up. All right. If we're at 75 at this dotted line, then each molecule of hemoglobin in your blood has given up one oxygen. All right. And then if it's down here at 50, they've given up 2. At 25, they've given up 3. And if we go to 0, they've given up all their oxygen. All right. So now I say here that at rest, because you're not needing as much oxygen, it turns out that really you do only give up one molecule of oxygen per hemoglobin throughout. And then you have billions and billions and billions of molecules of hemoglobin. So this really is a lot of oxygen. But what it's telling us is that there's still an awful lot remaining. And so this is a reserve. Okay? So the higher the partial pressure of oxygen, right? So here's our partial pressure. The more hemoglobin binds oxygen. So that's great, because in the lungs, it's right about here. And so in the lungs, as long as we have this partial pressure we mentioned, about 104, you bind, right? The lower the partial pressure, the more hemoglobin unloads, because that's really what we're looking at here, the unloading or dissociation. So when I go out into the body, right, and I really haven't got much of a decrease in partial pressure, well, hemoglobin is only giving up a little bit of oxygen. But here I get to this point at about 40, which is about average in muscles at rest, right? They are needing, right, oxygen. They've been losing this oxygen, so their partial pressure is lower. And because it's lower here, well, then the oxygen will leave the hemoglobin, right? And it'll move into the tissues. So this again means that oxygen is bound to the lungs and released in the tissues because of this relationship. And then the lower I went, which means more, the further to the left I go here, the more oxygen that is being used by the tissues. And of course, the more that's being used, the better hemoglobin will be at releasing it, dissociating it. It's a great, great protein. All right. So what else affects this binding of hemoglobin with oxygen? Well, go figure, pH and temperature and the amount of carbon dioxide even, right? So These graphs show this same basic sigmoidal curve and this idea, again, partial pressures. So the x-axis is the same and the y-axis is the same in all of these. But what we're looking at is we're describing the relationship if the pH is a 7.2, acidic, normal, or slightly basic. So the more acidic you become, right, and we shift this curve to the right, it means the more likely that hemoglobin will release oxygen. So the more acidic you are, the more oxygen released by hemoglobin. The higher your temperature, because here again is about normal, so a little bit higher, lower, lower. So, right, the higher the temperature, like pH, right, so pH lower, temperature higher, the more hemoglobin will release its, right, oxygen. And here you can just look at 40 here, and you notice that at 40 and at 43 degrees, you've almost released 2 molecules. And it's kind of similar here. You've noticed again it's about at 60% when you're at 40. But the point again is that you're meeting your needs. Why am I saying that? Well, because what does higher temperature indicate? Well, it indicates that you're transferring more energy, right? Because every energy transfer in the body is going to, on the earth in fact, is going to generate heat. So the more energy you need, the more oxygen you need, right? And the more heat you generate. And of course, the more you, right, need energy, the more carbon dioxide you produce, and the more carbon dioxide you produce, the more hydrogen you produce, and the lower the pH goes. So really what we're saying is that you're ventilating to meet your body's needs, right? You're moving gases to meet your body's needs. Your breathing rate and your depth increased with exercise. You'd think hemoglobin would also want to be able to change, and in fact it does. So pH and temperature have a direct effect. The higher the temperature, the lower the pH, the more oxygen unloaded. And then there's a variety of other factors that can influence this too. So now carbon dioxide, so we've gotten the oxygen and we're meeting the needs of the oxygen. So what about carbon dioxide? Well, it turns out carbon dioxide is moved 3 ways in the blood, all right? And we've got blood flowing through the systemic capillaries, always gaining carbon dioxide from these cells because the cells aren't metabolically active. And the more active they are, the more CO2 they generate. So we're typically going to see a higher partial pressure of carbon dioxide in the body than in the systemic capillary. All right? So we're going to move it. It's going to diffuse out of the cells and into the blood. And once it gets in the blood, it can do one of 3 things. It can dissolve in the plasma, because we said that carbon dioxide has a higher solubility, right? It can combine with hemoglobin, and again, it doesn't compete with oxygen in this case, right? But there is some influence here. But again, it's not a competing with the binding. So we can bind it to hemoglobin, right? Or, and this is where most of it, the way most of it is transported, is it is converted to a bicarbonate ion. So, and that happens because this carbon dioxide combines with water. Water forms carbonic acid. Carbonic acid dissociates into bicarbonate and hydrogen ions. So this is again why the pH can change if you increase carbon dioxide, right? More carbon dioxide can mean more hydrogen, and more hydrogen means lower pH, right? Well, it turns out that hemoglobin is a brilliant protein in as much as it even binds the hemoglobin. Binds the hydrogen. And because it binds this hydrogen, it actually prevents the pH to some degree from lowering under normal situations. All right? So we got to get this out from the cells. We need to remove the carbon dioxide. So again, we said driven by pressures. And this is elaborating. So there's our 3 ways. How do we do this? Well, it's always higher here in the cells than it is in the blood. All right, erythrocytes then. So these blood cells have this enzyme, carbonic anhydrase, which forms the carbonic acid. So it increases the rate of this reaction, making a lot of this quickly. This carbonic acid becomes bicarbonate and hydrogen. Again, what I said, the pH doesn't change because hemoglobin binds this hydrogen ion too and buffers the pH. There's a chloride shift that occurs, so this bicarbonate actually leaves, and I think that's the arrow here, leaves and is now present out in the plasma to help buffer other kinds of acids, and chloride enters, so bicarbonate out, negative, chloride in. and we're going to move back to the lungs.